Hello everyone, and welcome to our session on analyzing nested loops. Today, we'll explore how nested loops work, how they impact algorithmic performance, and what techniques we can use to optimize them. In this session, we will cover several key points. First, an introduction to nested loops and what they are. Then, we'll identify common patterns found in nested loops. We'll also perform a mathematical analysis of their iterations. There will be visual demonstrations to show you how loop behavior works in practice. Finally, we'll discuss optimization techniques and best practices to improve performance when using nested loops. Let's get started with the basics. Nested loops are simply loops that exist within other loops. They are often used to iterate over multidimensional data structures. Essentially, every time the outer loop executes, it triggers a complete execution of the inner loop. Let's analyze the iterations mathematically. When every inner loop iteration is independent and fully executed, the time complexity for two nested loops with constant bounds is O(n squared). Here's why. The outer loop executes n times. For each outer loop iteration, the inner loop also executes n times. Therefore, the total number of operations is n multiplied by n, which is n squared. You can refer to the iteration tree or matrix diagram shown on this slide, which clearly illustrates the n squared operations. Nested loops come in several patterns. Fixed bound nested loops, both the outer and inner loops run over fixed ranges, for example, from 0 to n1. Dependent bound nested loops, in this pattern, the boundaries of the inner loop depend on the outer loop index, for example, for j in range I, n. This creates triangular iteration patterns, which affect the overall complexity. And, of course, when you have multiple levels of nesting, such as 3 nested loops, the complexity increases to O(n cubed). An animation on this slide compares fixed and dependent bound iterations to help visualize the differences. Let's jump into the Visual Studio Code to see this in action. I'm going to implement a program that prints a multiplication table, which is a perfect example of a quadratic time, O(n squared) algorithm. The program prompts the user to enter a value for n. This value determines the dimensions of the multiplication table. 2 nested loops are used. The outer loop runs from 0 to n1, representing the row index. The inner loop also runs from 0 to n1, representing the column index. For each combination of row I and column j, the product I*j is calculated and printed. Since the inner loop executes n times for every iteration of the outer loop, the total number of iterations is n*n, which gives us a quadratic time complexity, O(n squared). After the inner loop completes, a new line is printed to start a new row, ensuring the multiplication table is formatted correctly. The structure of nested loops means that as n increases, the number of operations increases dramatically, quadratically. For example, if n is doubled, the total number of iterations increases by 4 times. This makes the algorithm straightforward but potentially inefficient for very large n. However, for typical multiplication tables, this approach is perfectly acceptable and clearly demonstrates the concept of quadratic complexity. In summary, this program is not only useful for printing a multiplication table, but it also serves as an instructive example of how nested loops can lead to O(n superscript 2) time complexity. Let's go back to presentation. Best practices and optimization techniques. Optimizing nested loops is key to efficient algorithm design. Here are some best practices. Loop unrolling. This technique reduces overhead by performing multiple operations in a single iteration. Early termination. Incorporating break or continue statements can help skip unnecessary iterations. Algorithmic improvements. Sometimes you can eliminate the need for nested loops altogether, for example, by using hash maps for lookups. Profiling and benchmarking. Use tools to measure runtime performance and identify bottlenecks within your nested loops. These techniques can dramatically improve the performance of your algorithms. Now, let's move to a visual demonstration. In this section, we will display an animation that shows the execution of nested loops, a graphical representation, such as a matrix or heat map, that shows iteration counts, visual comparisons that highlight how fixed versus dependent loop boundaries affect the total number of operations. This demonstration helps map the theoretical analysis to an intuitive, visual model of nested loop behavior. To wrap up, let's review the key takeaways. Nested loops significantly impact algorithmic complexity, often leading to quadratic or even cubic growth in operations. Different nesting patterns, like fixed versus dependent bounds, can alter the total number of iterations. Using mathematical analysis, you can predict performance, and various optimization techniques can help mitigate potential performance issues. I now welcome any questions or further discussion on nested loops, their analysis, or optimization strategies. Please send me the question using comment box. Thank you for your attention.